on this computer. Okay, so here we go. Well, share screen. My mouse is stuck on my pad. Let me minimize that. Okay, so wood structures. So today we'll talk about floor joists, and of course we're talking about lumber floor joists. Alex talked about engineering joists. I'll talk about a bit of that next week. And basically, I hope you can all hear me properly. I'm sorry, I got a bit of a cough in my throat, but I hope you can hear me a little properly. So
All good there.
it's all good. Thank you. Okay, so here we go. So now, first of all, lumber joists. We know what joists are. These are members that are put, fairly close together, spaced fairly close together, and they usually put in to support a floor. As opposed to, you can do the same thing on the ceiling, but those are called rafters, so they have different names, but they basically do the same thing. Now, sawed lumber used as joists range in thicknesses from 38 to 89. So in other words, you can have 2 by something or 4 by something, okay? And in depths of 89 to 286. So in other words, 2 by 4, 2 by 6, 2 by 8, 2 by 10, 2 by 12, or 4 by 4s, 4 by 6. But the 4s aren't as readily available as a 2-inch are. So let me just, where's my annotate? Okay. So in other words, guys, it's very simple. Okay. Now, keep in mind, this is a cross-sectional area of your floor joist. So in other words, the most typical one here is a 2-inch. Okay. Now, keep in mind that in imperial, this is a nominal dimension. What that means is that it used to be 2 inches way back when they first started making the joists. In other words, the members were actually 2 inches wide by 6 inches high. And over time, they kind of like got smaller and smaller. And now what the manufacturer does is, or the sawmill does, is that all the waste that the saw creates to cut these lumber size, that's already taken away from the member. So this is actually, this is a nominal size in imperial. And when they say that this is a 2 by 4, well, this is not really 2 by 4. This is 1 inch and 1/2 by 3.5 inches. So in imperial, these are the actual sizes. When you say a 2 by 4, these are the nominal sizes. But in metric, they actually use the actual dimensions. So in metric, this would be 89 millimeters, and this would be, this would be 38 millimeters, and this would be 89 millimeters. So when you see the values in the tables, those are the actual dimensions in metric, versus when we say a 2 by 4 or a 2 by 6 or a 2 by 8 and a 2 by 10 and a 2 by 12. Well, those are all nominal sizes. They are, if I'm off the top of my head, this is 3.5 inches, this is 5.5 inches, this is 7.25, this is 9.25, and that's 11.25, if I remember correctly. But I know that in metric, this is 89 and so on, 140, 180, and so on. And these are the actual dimensions of the lumber. But when you go on a construction site, you don't tell the carpenter, hey, give me that 38 by 89. He won't even understand what you're saying. If you say, give me that 2 by 4, he'll know what you're talking about. Okay. So these are the sizes. And like I said, very rarely do we talk about the 4-inch one. The most common one are the 2-inch width by the depth. Now, availability. Now, the thing is that in Quebec, okay, here in Quebec, what we do is we tend to use lumber that is readily available. And in Quebec, there's basically, okay, first let's talk about grades, okay? Now, this is what they call visual grade, okay? These are visual grades. What that means is that when the lumber comes off the assembly line, okay, or the production line, there's a grader sitting at the end of the line. He takes a piece of wood, he looks at it, he determines at, I don't know, in a second, he determines whether it should be considered structural select, number 1 or number 2. Number 1, number 2, or number 3 grade. And then he puts a color marking on, he has this color marking, he strikes against the board, and then the sorting machine either sends it to structural, select structural, number 1, number 2, or number 3 stud grade, okay? And this is all done visually, and these guys just sit there, and if you want, these guys get trained, and they have to look for different types of defects to determine whether it's going to be considered select structural, number 1, number 2, or number 3. So all the lumber that you see that has this stamped on it, these are all been inspected visually, as opposed to machine stress rated, where the piece of wood goes through this machine at every 6 inches, it gets loaded with this, well, gets loaded, that's machine stress rated, and these things run at about 1,000 feet per minute, okay, that's how many boards it can check, and that allows a more accurate way of grading the wood, and of course they increase the resistance because it's got a little bit more reliability on how strong the wood is. So that's machine stress rated, but most of the lumber you see in the lumberyard is still all visually graded. In other words, it's just one guy looking at the piece and determining whether it's select structural, number 1, number 2, or number 3 stud grade, okay? So this is the grades, and of course, this is stronger. This is the strongest visual grade. This is second strongest, and so on. That's what the grades stand for. Clear the drawings. Now, in 38 millimeter, 2-inch thickness, the most readily available material in Quebec is number 1, number 2, and the species is SPF. So if you ever go, next time you guys go to wherever you want to go to, Reno Depot or the Home Depot or Rona, wherever there's a lumber yard, okay, if you guys happen to walk down the aisle where they stack the lumbers, go take a look at it. And you'll be able to see on the lumber, you'll be able to see these stamps, okay? And on the stamp, you'll see the species. If you see SPF, that means that piece of wood comes from a tree that was either a spruce, a pine, or a fir tree. And number 1 and number 2, that's the visual grade that the inspector gave it, okay? And of course, if ever you're doing anything in Quebec, okay, when it comes to floor joists, you should not be specifying select structural. You should be specifying number 1, number 2, and of course, the species is SPF, spruce, pine, fir. Now, guys, we'll talk a little bit more about species later on, but right now, I'm just going to talk about SPF. And as a matter of fact, for the rest of this course, the only species that we'll ever use when we're designing something will be SPF. In certain cases, we're going to be using number 1, number 2, and in certain cases, we're going to be using number 3 stud grade. So, but this, as far as species goes, in this class, we'll only be using SPF. Like I said, it's the most readily available. Now, if you were in Vancouver, well, it would be the other way around. In Vancouver, they have a lot of Douglas fir, and therefore they fabricate, or they make the sawmills make a lot of their lumber out of Douglas fir, and therefore out there you wouldn't be using SPF, you'll be using Douglas fir, and that's because it's readily available in the forest as well as at the lumber yards. Okay. So now I want to talk about, when we're talking about wood structures, okay, there are 2 systems that we have to, or we can take into consideration that can help us in increasing the resistance of the members that we're going to be using. Now, I'm going to take this slowly, okay? Case 1 system. Now, this is a system. Case 1 systems are composed of 3 or more essentially parallel members. Now, what does that mean? Is that if I'm framing something, for example, a floor, so this is a floor plan. If I put a floor joist here, and I put a floor joist there, and I put a floor joist there, and so on and so on. So, you know, like when you're having a floor, you're going to have at least 3 members, okay? Another one there. So if I have 3 or more essentially parallel, and of course, the carpenter is going to put these parallel to each other, okay? No more than 610 millimeters apart. In other words, the maximum spacing here is 24 inches, okay? So in other words, you can have 12 inches, you can have 16 inches, but up to a maximum of 24 inches. If you have a maximum spacing of 24 and you have at least 3 members, then you have a case 1 system. And in a case 1 system, what that does, it allows you to take the loads in the table and increase them by 10%. That's a case 1 system, okay? Now, So whenever you're designing a floor, if you know you're going to be putting down at least 3 joists in that floor, and they're going to be spaced no more than 24 inches on center, and so on. In other words, I'm going to be spacing about every 16 inches. I'm going to have at least 3 members. I have at least a case 1 system. That's the case 1 system. Now,
Sir.
yes.
So basically they divided the cases, like let's say if they're if they're let's say 16 inches apart, that means let's say case 2 or something,
No,
or
no, no, no. It's not this. The spacing is a maximum of 24 inches. I can have them at 12. What's important is I have at least 3 of them. 1, 2, 3. Okay? So in other words, what they're saying here is that if I have only one member all by itself here, okay, Omar,
okay,
when I load this member, that member cannot share its load with anybody next to it. So this becomes a single member.
okay,
You follow? Now, so when I only have one member, I design it as if it's one member, a single member. But now, if all of a sudden I have 3 or more members, if I happen to put a load here, well, that load can be shared by this guy. It can even be maybe shared by that guy, and so on and so on. Okay, so because of this load sharing between the members, you can increase the resistance of this member.
oh, I see. So it
You see,
becomes case 1
it
because
becomes a case 1 system, and then you'll see in the tables with a case 1 system, the values are different than a case 2 system. Okay.
okay,
So that's what it means. Like it's nothing to do with that 12 inches is case 1, 16. It's up to, like, in other words, if you're stupid to space, if you, let's say you have at least 3 members, okay, and you have 3 members, but you space them at 32 inches. We saw that last week. That sometimes you see a 32-inch spacing. I've seen my colleagues do this. Bunch of idiots. Even though they have 3 members, but because of 32, you have to design them as if they're single members. Do you follow? Because it exceeds 24 here. Okay, so if you space them at 32, even though I have 3 members that are essentially parallel to each other, but because they're spaced at more than 610 millimeters, I cannot take advantage of a case 1 system. In other words, there will be no more mutual sharing of the load. So that's why whenever you're spacing something in wood, don't go over 24. Stay up to 24 and take advantage of it that you have a case 1 system, which means you'll have some kind of load sharing and you'll be able to increase the resistance of your system. That's
okay,
all it is. Okay. Now, so that's the case 1. Okay. Now, case 2. Now, guys, don't panic. Okay. Case 2 up to here. Okay, is the same requirements as a case 1. All this, okay, is all the same as this. So this here, the difference between a case 2 over a case 1 is that not only do I have to have at least 3 members, 1, 2, 3, okay, essentially very. In addition, the lumber must be covered with a minimum of 9.5 millimeter panel sheeting. Now, panel sheeting can be plywood, can be OSB board, whatever sheeting you have, but it has to be at least 3/8 of an inch thick, okay, and fastened to the joist to provide a minimum stiffness equal to by providing 2-inch nails. I hope you guys know what a 2-inch nail is, okay, common nail, at 150 millimeters apart at the edges and 300 millimeters apart at the centers elsewhere. So this means, like, in plan view, here's my sheet of plywood, okay? Here's my sheet of plywood that I put on the floor. Okay, and I'm going to try to draw this properly so you guys can, okay? And here is the floor joist here. And then I have another one here underneath, okay? And I have another one, sorry, another one there. I have another one there. Anyways, like, in other words, I have all these floor joists here. So now what this means is that I have at least 3 members, no more than 24 inches apart. So I fulfill the case 1 system. But on top of that, what I'm going to be doing is I'm going to make sure the sheeting I put on top of here in plan view is at least 3/8 of an inch thick, 9.5 millimeters. And in addition to that, I'm going to make sure that here, 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 the nails do not exceed 12 inches, 300 millimeters, okay? And here along the edge, they don't exceed 150 millimeters. So along here, the carpenter knows this automatically, that here he's gonna be nailing them at every 6 inches or 150 millimeters along the edge here. And in between here, he'll nail them at every 1 foot. And that's, now, by doing this, what you're actually doing is that, I'm gonna draw it here. So here's the joist. I'm gonna go back to this color here. Oh, I better put this on mute. Sorry, guys. Just, there you go. Sorry, I forgot to put my phone on mute. And okay, so this, now if I draw a cross section here, okay, if I draw a cross section here, what happens is that, I'm just gonna draw it here, okay? So what happens here is that, here's the floor joist, and here's the other floor joist, and so on and so on, okay? So this is the floor joist, and then on top of it, you have the sheeting here. Okay, here's a sheeting that's sitting on top of the joist, okay? So what's happening here is, because you are, I'm gonna go to green, because that's what I used before. Because you're putting a nail here, okay? And the nail is gonna connect the plywood to the wood. You're actually, what you're doing is that you're now letting the plywood also contribute to the resistance of the joist, and therefore you are like creating a little bit of a T section from and so the plywood will contribute. So in other words, what happens here, I think you guys did this in your physics, where you had to calculate the nails of the wood stuck together, for shear flow. So
Yes.
what you're actually doing here is that, because you're nailing the plywood to this joist, you're getting now somewhat of a T section that's going to be helping you to resist the loads. And because of this, it also going to allow you to increase the resistance. So you're not just relying on this guy anymore. This guy is helping carry the load with this guy, and therefore that also is going to allow you to increase the resistance of this guy. Okay? But like I said, for you to have a case 2 system, you need the same criteria as a case 1 system. In other words, at least three members parallel to each other, and spaced no more than 24 inches on center, or 610. And then on top of that, for a case 2 system, so for example, all residential floors, you'll look that the spacing is never more than 24 inches. First of all, the general spacing for floors is always 16 inches, so that's okay. In a floor, you're going to have at least 3 joists in the floor. That's okay. Then you're going to have 5/8-inch plywood, which is the typical thickness for a subfloor. Wow, I need only 3/8. I got 5/8. And then if the carpenter is going to make sure that he nails it according to the schedule, in other words, one at every 6 inches along the edges, and one at every 12 inches at the intermediate centers of the joist, then you're going to be creating a case 2 system, and you're going to take advantage of that. And when you go to the tables, you'll be able to take the resistance for a case 2 system and not just a single member. Okay, and you'll probably become a little clearer when we go see the tables. Okay, so that's something I wanted to talk to you about. And that's what the thing about when you're doing some light framing with lumber, because members are spaced relatively close together, because of this load sharing, and because of the way that the sheeting can, be combined with the member themselves, well, they took advantage of that, and will allow you to increase the resistance of those members. So, this thing is in my way. Now, oh, that's not what I want. Okay, now, remember, what are we doing when we're designing? Okay, so when we're designing, we are basically, okay, we want to make sure there are, like we want to make sure the factored moment resistance MR is always greater than the maximum factored moment MF. We want to make sure the factored shear resistance VR is always greater than the shear force VF. Okay, now in the calculation, I don't even get into this. Okay, I don't care. This is very similar to what they're saying, is that if you're calculating the shear of a joist, okay, and it's sitting here, okay. I don't know if you guys remember in concrete where we took the force of VE at dV, okay. Well, this is what they're saying, that you can take the shear force here at a distance here of D to calculate what the force you have to take. I always take the shear force right there. So I don't even bother with that unless, and shear is not necessarily the one that's going to really affect the choice of my joist. So I never really bother with that. But if you want, you can take advantage of that. That's what they're saying here. I don't even bother with that. I only do that if I do happen to have a VR less than VF and it's right at the support, then I'll go check it what it is at D away and see if I'm still okay. Now, the the factor notch resistance of them, I don't even talk about this in this course. And just to give you an idea of what notches are, okay, these are notches. So in other words, if you are going to cut your member, okay, so that your member is sitting wherever it's being supported. In other words, these are called notches. There's a whole section on how to design for these notches. And since notching is a very, very unique situation, I don't waste time with that. I'd rather concentrate on what you're going to be doing 90 to 95% of the time in your wood design. So yes, if you have notches, you have to design for the notch, okay? And there's a whole section in the handbook. And if you guys ever get into notches and you need to design notches, just ask me and I will scan my handbook. Don't even buy it, and I'll send you the section for notches if ever you get into it, okay? Now, so that's why I don't even bother with this. And then, of course, the other thing you have to worry about is you have to make sure that the bearing resistance QR is greater than QF. So in other words, what you have to make sure of, and I'll draw it here, okay? So you have to make sure of that when it's sitting on a support, not for the notches, but when the member is sitting on a support, like for example here, okay? When the member is sitting on a support, okay? This is called bearing, and you have to make sure that the length here is sufficient so that the wood does not crush. And we will be doing that today to check that, or what is the minimum length you need in order for that not to crush. We will check for bearing, and at the same time, we will check for the maximum deflection under specified loads. In other words, we will make sure that the ESI, okay, provided is greater than the ESI required, okay? And we'll be doing that in our calculation. So these are the design objectives. And of course, in our designs, we will check for this, we will check for this, we will check for this simultaneously. And then after that, once we selected our member, we will go check what the bearing length will be. And that means our member will be designed. And we'll be doing that today. So clear all drawing, okay? So now, what I want to get into is this, okay? Now, don't panic. The resistance for joists are based on the following formulae and factors, okay? So this is the formula that if you want to calculate the MR, the same way we did for a beam in concrete, if you want to calculate the MR for wood, well, this is the equation, okay? And not only is this the equation, but this part of the equation, this is the value for that. So it can get pretty hairy, but we will be talking about these factors. This is important. So this we will know, talk about, and understand them. So this is just for MR. The same thing happens for VR. So here's the equation for VR, but the big VF here, here's the small VF. So the small VF and all of these factors. And then of course the ESI is called the stiffness, okay? The stiffness of the is based on these, like it's based on these factors here. And we'll talk about these, the actual stiffness, in other words, the modular elasticity and the moment of inertia. And of course, I don't talk about notches, okay? So here's are the equations, okay? And I'm pretty sure that if I would even go through this once, nobody would even bother remembering. So I just telling you that these are the equations. If you wanna, get very analytical, okay? This is what you do. You take the equation, then you go find the values. You go find this value here. Well, this we will know. We need to know these because of the tables. And then after you go through the whole equation. Or you can do all of that, which I don't think is a smart way of doing it. Uh, we can do all of that, or we can simply use this. Isn't this faster? Okay. So this here, guys, is the joist selection tables. Now, this one here is of course for a 38 by something lumber. Okay, I'm gonna take my time here because this is something that, okay, first of all, let me just talk something, okay? Here are the grades. This is select structural. Here's number one, number two, okay? And as I said, very rarely will a lumberyard have select structural, so we will never be using this table here, okay? I don't recommend you even consider using this table here. That's number one, okay? Number two, these are the species of wood. Now, guys, you do realize that there are many types of woods out there, or trees, okay? And each tree, well, first of all, lumber is made from softwood, and I hope you guys learned somewhere what a softwood tree is versus a hardwood tree. The softwood tree are the ones that stay green all year round, and the hardwood trees are the ones that lose their leaves. Okay, so one is a softwood, the other one's a carnivorous and deciduous tree. So all the lumber that we have is made from softwood, in other words, trees that stay green all year round. And within those trees, here are the species. DFFIR, this is a Douglas fir larch, this is an abbreviation. Hemlock fir, this is a northern species, okay? And of course, this is what we're going to be using 100% of the time, because this is the most common species that we have here in Quebec in our forest. We have spruce, we have pine, we have fir, okay? We do have some northern, but this is the one that's the most common with the woods around us. So we will always be using this section of this table. So that's why it's pretty useless. Now, here is, of course, the grade. Here
Sir,
is,
sorry, I have a question. So the
yes.
Douglas fir one is the one they use in the most in British Columbia.
Yeah, because you go to British Columbia, it's unfortunate. I forgot. I had a nice picture because I go there because my son lives there. I had this beautiful picture of a Douglas fir. I wanted to share it with you. If I remember, guys, I'll try to show it to you next week. Okay? Yeah, in British Columbia, one of the most common trees that you have out there is Douglas fir. You have some larch also, but the most common one, and you have a lot of cedar also. But cedar is not used to make lumber. Cedar is used for other reasons. Okay, but as far as in British Columbia, Douglas fir is very, very abundant, and therefore the lumber as well as the plywood is mostly all Douglas fir. Okay.
Okay, thank you.
Okay, that's why. And then here, if you go into a lumber yard, you're going to look on a piece of lumber. Okay. There's always, the lumber always should have a stamp. Okay. And on that stamp, you're going to see uh, the species, you're going to see the grade, and it's going to tell you whether it was dried or if it's still green. And we'll talk about that also later on. Okay. Dry and green wood. But right now, I just don't want to put too much on your plate. So now this here, so let me clear this drawing so that it'd be a little bit clearer. Okay, so here, like I said, this here, no good. This here, if you go out to BC, you'll be using this, okay? Here in Quebec, we use this. This is the one that is the most readily available, okay? And of course, so here's the grade, here's the species, that's number, okay? And here's the size. So this is a 38, this is a 2x4, a 2x5. These are hard to find. So don't even bother with this. I don't even consider this in my design. This is a 2x4, 2x6, 2x8, 2x10, 2x12. Okay, so this is a 2. This here is 4. I should have put 4, 6. It goes up in nominal dimensions of 2, 8, 10, and 12. Okay, so this is a 2x4, 2x6, 2x8, and this is a 2x5. Very rarely can you find 2x5. So I don't even consider that. Now, so here are your sizes. Now, this is the value of a single member. So in other words, if I have just one little member out there carrying all the loads, well, I would have to use the values here. This is for a single member. Now, if I have a case one system, in other words, I have one piece here, one piece here, one piece here, and there are at least 3 pieces generally parallel to each other, spaced no more than 200 feet apart. This is what they're telling me. For case 1 system, take the values of a single member and multiply it by 1.1. In other words, increase it by 10%. So if I have a case 1 system, I would take, for example, if this is my MR value, I would take 4.09. If it's a case 1 system, well, I would multiply it by 1.1 to get my MR value. Okay, that's what they're saying. Now, look at a case 2 system. This is where you have those 3 members put together and you have your plywood on top of it and you have your nailing and all that. Look at the difference in the MR value. Okay, let me just clear this again. Look at the difference in the MR value. Let's take something simple between, okay, 2x4. We don't necessarily use 2x4s for joists, but still. Look at the difference in the MR value for a 2x4 for a single member versus a case 2 system. Okay, it increases by 40%, guys. Does anybody have a calculator? I'm going by memory. Does anybody have a calculator? Take 9.08 and multiply by 1.4, or take any of these numbers here and multiply by 1.4, and tell me if this is what you get here. Because I think, has anybody tried it?
Yeah, it's pretty on point.
Yeah, exactly. So in other words, from a single member all the way to a case 2 system, because of the plywood, helping and carrying the load for that piece of lumber, they were able, by tests and everything else, to determine that you can actually increase the resistance by 40%. Isn't that nice? Okay. So when you can create a case 2 system, it's very beneficial. So in other words, you'll be able to select a smaller member to carry the same load. Okay. Now, so this is the value of MR. This is the value of VR. Okay. And of course, that's for a single member. This is the calculate MR, VR for a case 2 system. Now, if you happen to have a case 1 system, you take these members here and you multiply them by 1.1, just as you see here at the bottom of the table. And if you know automatically you have a case 2 system, in other words, if you're designing a floor in a building, in a house, you're going to tell the carpenter you're going to specify the nailing schedule in your drawing so that he puts a nail at every 6 inches along the edges and at every 12 inches in between the supporting members. And therefore the nailing you'll make sure that the nailing meets the requirement of a case 2 system. You'll make sure that it's at least 3/8 of an inch thick, the sheeting material. I don't care if you use OSB board, I don't care if you use plywood, and so on. And if you're going to be using planks, well, they have to be at least 19 millimeters in thickness. Nobody uses planks anymore. And therefore, you'll be able to go straight to the table and get your MR value for a case 2 system and a VR value. Now, ESI, okay, this is called the stiffness. So EI, okay, now they put an S here because it's in service, okay, because you'll see later on there's a different E for compression, okay, in service. So the modular elasticity multiplied by the moment of inertia is called the stiffness of a member. And this is the same whether you're talking about wood, whether you're talking about steel, whether you're talking about concrete, okay? So the EI value, when people say how stiff is the member, well, it all depends on the modular elasticity and it depends on the moment of inertia. A high modular elasticity and a high moment of inertia is going to give you a very, very stiff member. A low modular elasticity and a low moment of inertia is going to give you a very, very, flexible moment of inertia. So that's the stiffness. And when we're designing for serviceability, this is where we check to make sure the values that we need are provided from here. Okay, so that's the stiffness. And of course, the units work out because when you'll see the formula later on, you'll see why these units work out. So here, the units are in kilonewton meter for the moment, which is of course the right units for a moment. For shear, it's in kilonewtons, and of course, for the ESI is in Newton millimeters, and you'll see why that's in Newton millimeters squared. Does anybody have any questions on this table?
No.
I guess no.
Is it clear how to use it?
Yes.
Yeah, it's clear, sir.
Oh, we'll see when we do the exercise.
Exactly, but I'm just telling you, when we do the exercise on my PowerPoint, I extrapolated just this part of the table. You understand? So, because that's the part that I always use. So I don't call up the whole table. If you want, we can call up the whole table, but you'll see in the example, I just use this part of the table, okay? Because that's the part, like I said, you should be using here in Quebec, and that's the part you should be using all the time, even if you, for the rest of your life, if you're going to be designing wood in Quebec, unless we start planting different trees for 30 years from now. Okay, so we'll see. We'll apply it to an example exactly, and that's okay. So this here is, of course, something we're going to use very often in this course, okay, for the floor joist and for other reasons later on. I won't get into right now. Now, here is what I love about the handbook, okay? Here, what I love about the handbook is that in order for you to be able to take the value from the table and use it to design with, the handbook gives you this checklist, okay? Now, so to verify that the tabulated resistance, okay, in other words, the MR value, the VR value, and the ESI values are appropriate for the structure being designed. In other words, if you want to use the design values that are in that table, the following question should be asked, okay? The appropriate modification is given in brackets. Now, is the load duration standard? And we're going to talk about this on the next slide. So in other words, I'll explain to you what a standard load is, okay? But I want you to, what I'm trying to stress here is, can you try to remember this? K, okay? And look, there's a subscript D, and of course the D is for duration, okay? Now, is the service condition dry? In other words, S, okay? So remember, S is for service. In other words, are we in a dry condition or are we on a wet condition? Because wood does not happen to act the same if it's dry or if it's wet, okay? Is the material free of incisions and or strengthening reducing chemicals? In other words, is the wood treated? Yes or no? So KT for treated wood. And I don't care, we will not use any notches, okay? Does this construction provide lateral stability for the joist? So in other words, if I have a joist here, okay, and I have a joist here, and I put plywood on top of it, and I'm nailing the plywood to the joist, and then the end of the joist are nailed into a header joist. Yes, my joist is fully laterally supported. Okay, so therefore I can use the table. So as long as you got a floor condition where you have a header joist or you have plywood, okay, then you can say yes to the fifth question. So therefore, this is automatically yes, because I will be laterally supporting my joist with the sheeting and also and so on. So is a low, if this is yes, if this is yes, if this is yes, if this is yes, they're saying if the answer to any of this question is no, okay, then we'll have to do something, and I'll show you what to do in an example. If it's yes, go straight to the tables and take your values, okay? And I've got two examples. One where we say yes, 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 and we go straight to the table. And I have another example where we're going to say no, 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 and yes for the last one because, you know, and then we're going to have to do something, but I'll show you how simple it is to do that modification. So don't worry about it. But like I said, this checklist, I love the handbook for this because for every table that the handbook has, it has these checklists. And all the tables that we're going to be using that I took from the handbook, I will be showing you this checklist. So there's one for joists, there's ones for beams, there's ones for columns, and so on and so on, okay? So this is, but what we're going to talk about now are these factors, okay? KD, KS, KT. We won't talk about KN. We won't talk about this. KL is just stability. Like I said, our joist will be laterally supported by the sheeting and so on. So now, so this is our checklist, and oops, this is KD, okay? So this is just for load duration, okay? Now, in terms of load duration, there are three possibilities, okay? Three possibilities for load duration. Like how long is a load gonna stay on my structure, okay? Now, what I like about wood is that you have what we call a short-term duration, Okay, now what is short term? People say, well, wind blowing on your structure is very short term. Okay, so that means that wind, if you're designing for wind and you want to take advantages, you can take a KD value of 1.15. In other words, you can actually increase the resistance in the table by 15%. Now, short term means that the construction of the loading where the duration of the specified load is not expected to last more than 7 days. Okay, in the very last lecture we're going to do in this course, we're going to be designing formwork. Believe it or not, when you pour in concrete, within 7 days, the concrete structure starts supporting itself. Even the concrete that you place on your formwork is considered to be short term. So when we're going to be designing the joist, we'll be taking advantage of this KD equal to 1.15. So what does that mean? Is that if I take the MR value from the table, okay, I take the MR value, I can actually increase it by 15%, and that will be the actual MR value that I can use in my design. Okay, so for short-term loads, you can actually increase the resistance. Okay, so that's what that means. Standard term. Well, in most cases, if it's not short-term, okay, in most cases, standard means the conditions of loading where the duration of the specified load exceeds that of a short-term load, but is less than the long-term load. I like the way they define this. Okay, this is very nice. Okay, in other words, standard is in between here and here. Yeah, I agree. Okay, examples. So this is where you can relate to it. Examples of standard loads are snow loads, live loads due to occupancy. So when you're designing a floor in a house or in a building, that would be a standard load. If you're designing the structure of a roof, that would be a standard load. Okay, because the snow load can be there or can, you know, melt away and can pile up and so on and so on. So you don't consider it to be a long-term load. Okay, so standard loads, so all the occupancy loads that we have in the building are standard loads. The snow loads is a standard load. Okay, and even the dead load that's combined with the variable load of snow and occupancy loads, even that dead load is considered to be part of the standard load. So in that case, all the table says is that all the values that we have there were meant for standard load duration, where therefore the KD value is 1. Okay. Now, long term. Now, this is something I want to stress. Okay. Long-term duration means that condition of the load in which the member is subjected to more or less continuous specified loads. Now, examples include dead loads and dead loads plus live loads, such as characters that are imposed on the member for a long period of time as a dead load themselves. Such load includes usually tanks. So in other words, if you're designing a tank where you're going to have a fluid sitting in there for 3-4 months, don't consider that to be a live load. I'm sorry, not a standard load. It is a live load, but take it as a long-term load, okay? So if I'm going to be designing a warehouse and I know the guys are going to be stockpiling stuff in that warehouse and it's going to be staying there for months on end, well, I will not use, even though the stockpiling on the floor is considered a live load, okay, that's the live load, but the load factor for that, I would consider it to be 0.65. In other words, I would take it as a long-term load, and therefore all my MR values, okay, would be multiplied by 0.65, and they would get reduced. So the long-term effect of these loads, I've already compensated by reducing the actual resistance. So the longer the load stays on, the weaker you should take the resistance of the member. And how do you do that? Well, you multiply it by this factor here, 0.65. So if you have a warehouse, even though the stocking of the stuff is considered to be a live load, it's not the type of load, it's how long the load will stay on your structure. If it's going to be there for 2, 3, 4 months, well, consider, or for example, if I'm going to have a piece of equipment, if somebody's going to be putting a big generator on the floor, okay, that generator is going to be a long-term load. It's going to stay there forever, and therefore in that particular area of the floor, I might consider a KD value of 0.65 to design the members that are going to be supporting that particular load. Okay, so load duration is the length. Okay, so short-term, wind, formwork, and so on. Earthquake, short-term, wind, short-term, okay? Formwork, short-term. Standard is most of the stuff is standard. In other words, occupancy loads, snow loads, and so on, those are standard loads. only when you know that even though it's an occupancy load and it's going to be there for a long, long time, you might consider that to be a long-term load, and therefore you might consider using a KD equal to 0.65 for your design. Okay, so this is just load duration, and we're going to repeat this over the whole course, the whole semester, these load factors, and I'll show you how to apply them in your design. So that's just KD. Okay, so D is for duration, K of course is the factor. Any questions before I move on?
No.
No? Okay, so everybody understand duration, short, standard, long. It's nothing to do with live, snow, or whatever, okay? It's got to do with time. How long is the load going to be staying on your member or on your structure? Now, that's KD. Then after that, you have KH. KH is a system factor. We talked about that, okay? And therefore, KH is either case one, okay? In other words, 3 members or more, space no more than 200. So KH is a system factor. And for a case one, you multiply all the values by 1.1. And then for a case two, all the values get multiplied by 1.4. So, and we just proved it to ourselves. When we were at the table, we took a single member and we multiplied all those values by 1.4. We had the same values for a case two system. So the table already has the case two system multiplied for those MR values. So the table is incorporated in the tables as noted. So you don't have to do nothing there. Just have to know whether you are going to have a case two system, or I'm going to have a single, or am I going to have a case one. Well, for a case one, take the value of a single member, multiply it by 1.1. And you see that footnote at the bottom of the table. So that's the systems factor we've talked about. Now, S for service conditions. Now, what kind of service conditions you can have? Well, there's basically only two. Okay, the wood could be in a wet condition, the wood can be in a dry condition. Okay, in other words, if the wood happens to be subjected to dry service conditions, in other words, when I build a house, hopefully the envelope is going to keep my wood nice and dry. It will not, get wet, and it will not stay moist, and so on. Okay. And people have asked, it says, what is considered to be wet wood? Okay, wet wood is when the moisture content exceeds 26%, the wood starts to be wet. Okay, even up to, like, for example, when you're buying lumber, the National Building Code requires that all lumber that you buy at the lumberyard, the moisture content does not exceed 19%. Okay, so most of the wood in your house right now, okay, if your house has been built and it's gone through one heating season, okay, the moisture content of the wood right now in your house, depending on the winter, of course, is drier, so therefore the moisture content is going to be lower, but that should be about 5 to 7%, 8%. Okay. And of course, you can buy these little what do you call them, moisture meters, and you can just punch the wood and get the moisture reading. But if you want to know, like, it's based on, like, is my wood going to stay below 19%? If it's yes, and it's going to be stay like that for the rest of its life, then it's considered to be a dry service condition. If it goes over 26%, then you should consider it to be a wet service condition. And depending on what kind of conditions your wood is going to be subjected to, then you have to modify the values in the table. So here is for
Sir?
what, yes.
So what I know is that in each place in each country, they have like a percentage of the moisture. Like, let's say we're wet climate, so our, I think, regulation for the wood would be different from, let's say, California, because like they are not that wet climate. Do you know like the percentage of that, like which range or?
Look,
Okay,
between you and I, okay? If I build a wood structure in California, or if I build it in Florida, or if I build it in Canada, or if I build it in BC, okay? If it's inside of a building, what's going to be the service condition inside of a building?
should be dry.
Exactly. So like, it's what condition is the wood going to be in under its life expectancy? So inside of a building, you should assume that it's going to be dry, because if the building gets abandoned, you don't care. Nobody's living there. If it happens to collapse, nobody's going to get hurt. Okay, so inside, like as far as serviceability goes, it's either going to be, I can have inside of a building, okay, I, for example, have a wooden floor and the guy's going to be stockpiling fish all the time on the floor. What kind of a service condition should I consider?
Wet. I don't know.
Exactly, wet, because the fish, he's going to throw the ice in there, he's going to throw the fish in there. 99% of the time, that floor is going to be wet. You see? So don't look at it outside or inside. Look at in what environment is your wood going to be subjected to once it's in service. Is it going to be in a dry environment or is it going to be in a wet environment? Of course, if you go outside, believe it or not, my wood outside for my balcony, right? I still consider that to be a dry condition.
Okay.
Why? Because it's going to rain, but it's going to dry up right away. When it snows, it doesn't penetrate the wood, so it doesn't wet the wood. You see, so even outside, I might consider it to be a dry condition.
Even if it's very humid, like Florida?
Even if it's very humid, as long as the moisture content, even if it becomes very humid, does the moisture content go over 26%? No.
I'm not sure, that's why I'm asking. Okay, it doesn't.
It doesn't. You understand? Like, so just because it's super humid. Now, if all of a sudden it's like, I mean, like I've you know, I own a house there, and I can tell you in the summertime when I go touch a piece of wood outside, it's not wet in my hands. It's still dry. Yeah, the moisture content goes up, guys. The reason why I take 26% is because that's the, let's call it that's the moisture content that when it goes above that, it's considered to be wet. And then what happens is that when wood goes above 26%, and then all of a sudden it loses moisture content and it goes below 26%, 26% is that barrier, or let's call it that threshold. I shouldn't say barrier, but it's that threshold that causes wood to rot. You follow? But that's got nothing to do with strength. What happens is that when the fibers get wet, they don't have the same strength to hold themselves together than when it's dry. So that's why the wet service condition happens to allow, or asks you to reduce the strength of your wood. Okay, it's got nothing to do on its durability. Okay, so that's all you have to keep in mind. So if I'm going to have, for example, if I'm going to have a piece of wood, like guys, if I can have a piece of wood that is submerged in water, okay, and if it stays submerged in water and the moisture content doesn't change, it will never rot. Do you know that?
What? Can you repeat that? Sorry.
When I take a piece of wood and I put it in the water and I leave it in the water, it will never rot.
I didn't know that. Because it doesn't dry, you mean?
It doesn't go through that change of more than 26%, less than 26%, more than 26%, less than 26%. Do you follow? Guys, in Venice, okay, in Venice, they used to, what they used to do in the old days, okay, in Venice, they used to take timber, okay, I don't know if you guys know this, but they used to take timber and lay the timber on, like this, logs, right? Logs, big logs, and they used to lay the logs in the mud, and they used to make a raft with the timbers, like this, okay? You understand? And then they would build the pier of the bridges in Venice on top of these timbers, okay? They went to repair one of the piers of a bridge that was 400 years old. When they got down to the mat, to this raft, sorry, I should have made it round. When they got down to the wood that was supporting the pier, all the logs were in the same state, almost in the same state that when they placed them there when they built the bridge. They didn't rot. I don't know if you guys ever noticed, like when you go to, like, let's say you go to a seashore somewhere and they have wooden piles going into the water. I don't know if you ever noticed this. Here's the water, okay? And then all of a sudden, I don't know if you guys ever noticed this, but next time you go to a beach and you see these wooden piles in the water that holds up the docks or the wharfs, I don't know if you've ever seen this, but if ever you go, if this is the low tide and this is the high tide, okay? Everything below low tide hasn't rotted. Everything above high tide hasn't rotted. The rotting always occurs between here, where the water fluctuates up and down. And that's where these wooden piles are going to start rotting. right where the low and the high tide, in other words, where the moisture content keeps constantly changing day to day. Otherwise, everything below the wood stays nice and, and everything above the high tide stays nice. So it's only where the wood goes through moisture changes that it breaks down the wood cells, or yeah, the wood cells, okay, and causes the wood to rot. Otherwise, the wood would stay, perfectly fine. Okay, so that's just some general information for you guys to know about. Okay, so now what's more important here is I want you to understand what serviceability means. Is that, are we in a wet condition or are we in a dry condition? Not necessarily outside or inside. It can be inside wet, we can be even outside, we can be dry. Okay, so that's what I'm trying to stress here. Now, so whenever you're doing some bending, okay, so KS, service for bending, in other words, your MR value, if you happen to be in a wet service condition, all the values in the table that you see in that table have to be multiplied by 0.084. That's what they're saying. So if I have a wet service condition and I want to get the value of MR, take the value of MR in the table and make sure I multiply it by 0.84 to get the real value of MR under wet conditions, okay, for bending. SRB is for bending, okay? Then you have for shear, you take the values in the table and you just reduce them by 4%. In other words, you take 96% of that value for shear, but this is for shear, okay? Service for shear. And then for, okay, this here, I put it in, but we'll never talk about that. This is for notches. We won't talk about that, but I put it there anyways, because in case you ever get into notches, remember there's even a factor for notches. And of course, this is for serviceability, in other words, for bending. So when I want to calculate my ESI value that I need for bending, I have to take the values in the table and multiply it by 0.94, okay? So this is just for, so what they're saying is that all the values have to be reduced. By how much? Well, am I talking about bending? Am I talking about shear? Am I talking about stiffness? For bending, 0.84. For shear, 0.96. For serviceability, for stiffness, 0.94, okay? So all they're saying, take the value in the table, multiply it by this. Take the value in the table, multiply it by this. Now, you guys don't have to memorize this because it's an open book exam. Just make sure you know where to get access to this information, and that's it, okay? So don't, I mean, I know some of these by heart, but even when I know something by heart, guys, I always take the time to go back to my textbook and check to make sure I don't accidentally use the wrong number. So I don't expect anybody to memorize these. I just expect them to know what they're used for and when to use them. Okay, so that's for serviceability. Now, KT, what do you think the T stands for? Treatment factor. Do you guys has anybody ever seen treated wood?
Yes.
Yes, of course.
Okay, so in other words, when wood gets treated, it loses its strength.
They compress. They put it in a pressure room, like they pressurize it.
They
right?
can either pressurize it, okay, or they can do this to it, okay. They can pressurize the treatment, or they can have incised. Now, has anybody ever seen incised lumber?
Nope.
No.
No, sir.
Okay. So this is incised lumber. You see? So what they do is they make holes here. What do you think they make all these holes for?
So the water evaporate from the wood.
No, so that the whatever they're using to treat the wood can penetrate more into the wood. Okay, it allows the wood it allows the treatment, whatever chemical they're using to treat the wood, it allows it to penetrate further into the wood. You see?
Yeah.
Okay. Now, what happens when you do these little, when you do these incisions? Okay. Well, it damages the surface of the wood, so therefore it becomes weaker. Okay, so instead of having all these fibers here working and bending, well, this piece of fiber is gone, this piece of fiber is gone, this piece of fiber is gone, that's gone, that's gone. So when you're treating the wood and you got these incised lumbers, well, you have to reduce the MR value. And that makes sense to me. Not only that, the chemicals themselves can affect the fiber. In other words, it can weaken the fiber. Okay, so KT can either be just the chemical itself, or you can have these incisions that actually will damage the fiber, so therefore the piece of lumber is weaker. Okay, because guys, remember, okay, if this member was in bending like this, okay, it's these fibers here on the outside, or I should have put in the right direction. Okay, okay, it's these fibers right here at the top and these fibers right here at the bottom that are, you're actually calculating the limit of their strength to. So if I start making little holes in here, well, I'm starting to take away some of those fibers that are going to give me that full resistance. And that's why you have to take the MR value in the table and multiply it by the KT factor when you're having treated wood. Okay. So these are incised lumbers. And next time you go to the lumber yard, you may see this. Sometimes you don't see the incisions. It's just a chemical, okay? Like somebody said, it's just pressurized into the lumber. And sometimes you have incisions. It all depends on the person that's treating the wood, how he wants to do it. And of course, this is the machine that, you know, they just run the lumber under and creates all those incisions in the wood, okay? So, okay, so that's the, okay, now KT, well, here you go, okay? KT for MR and VR, there's only one. It doesn't matter whether you take the MR value or the VR value, the KT factor is the same. So for dry surface condition, even though it's dry, okay, if you're using a treated wood, you have to take only 3/4 of the value of in the tables, whether it's MR or VR, if you're using treated wood, okay? And look at this. When it's wet, it goes up. Isn't that amazing? Why do you think that when it's wet, it makes the wood stronger when it's treated? When I saw this the first time, I said, that's interesting. Dry, I take only 3/4 of the value in the table. When it's wet, ooh, I take 85% of it. Isn't that interesting?
So is it because when the liquid hardens, it becomes stronger?
No, it's because the water dilutes the chemical that affects the fiber. So under wet surface condition, it dilutes the effect of the chemical that they put to preserve the wood. Does that make sense?
Yeah.
Okay.
Yes.
That's, you know, and when I saw it the first time, I said, wow, that's interesting. You know, that's, you know, like, guys, this is what these are my like wow moments. You know, I think about, I ask myself, why is this under dry smaller than when it's wet? And then in the back of my mind says, well, the water must help to minimize the effect of the chemical on the fibers. That's what I thought it was. You understand? Anyways, now the KT, now don't forget, this is for bending, MR and VR. Okay, so these are the values. Now, when you're looking, now this is just for the stiffness, the KT value, okay? For dry surface conditions, you take 0.9, and for wet surface condition, you take 0.95. So this is for the ESI values, and this is for the MR values, and this is for the VR values, okay? Now, if ever, guys, if ever, like these are suggested values, okay? If ever you have a fire retardant, okay, so in other words, the architect does not want to cover up his nice lumber with gypsum board or you know, some kind of fire resistant material, and he wants to leave it all exposed, but he's going to have the whole thing treated for fire. Okay, you guys, you call up the manufacturer, okay, whatever treated wood that you want to use, okay, call up the manufacturer and say, hey, what's your KT value? Give me your KT value wet, give me your KT value dry. Get it straight from the manufacturer. Don't guess, don't use these values. Always call up the manufacturer. They will tell you based on their, you know, what they've tested and the laboratories that tested their chemicals, what their KT value is, and that's the one you should be using in your design. These are suggested values, but whenever you're using any treated wood, you should always call up the person that's actually making the wood and ask him, give me your KT value, okay? So keep that in mind, especially for fire, because you don't know how badly the chemical is going to be affecting your wood. This can be, you know, completely different from what we have here. Okay, so guys, so we talked about KS, we talked about KT. Well, we talked about other things, okay? Now, size factor, okay? So guys, you know what they found in wood? This is amazing. I love this. KZ. Okay, I'm going to talk about this, but don't worry, this is already incorporated in the table. So size is incorporated in the table for the given dimension, so don't worry about it. Okay. What I found interesting in wood, okay, a 38 by 89 piece of wood, okay, is 70% has 70% more resistance. A 2x4 has 70% more resistance than a 2x12. See, you know what people always think. Okay, this is they found this by, of course, testing. Okay, they took a 2x4 like this, and then they took a 2x12 like this. Okay, they loaded a 2x4 and they loaded a 2x12. Even though it's the same species, the same grade, okay, or for example, okay, if I take a 2x12, it's everything's the same, okay, they found that the smaller the cross-sectional area of the wood, the more resistance it had. So what they've done is that they've come up with these size factors that will increase the value of MR, okay, as the piece of wood gets smaller, as the cross-sectional area gets smaller, okay. So you don't have to worry about these. These are already incorporated. In other words, in that big formula there, MR is equal to phi FB. That's already incorporated, and therefore the table has already taken all these values into consideration. So you don't have to worry about them. But I found this very interesting that for the same species, for the same grade, everything, the smaller the piece of wood, the stronger or the more it can resist the load. So for example, if you did it, for example, if I took a 2x4 here, okay, this is a 2x4, and I supported it here, and I supported it here, okay, and I put a load here P with a 2x4, the same span, and then I take a 2x12, okay, put a load there, I put a load there, and I put a load P. In other words, I take the same span here, L, the same span here, L, I take the same load here, P. You think that in terms of proportion, if you do everything in proportion of cross-sectional area, okay, this one, okay, should, like for example, this is a 38 by 89. In other words, this one should be able to, like a 2x4 versus a 2x12. This P should be, you know, 3 times the P here should give me the thing to crush for the P here. It turns out that it's not in proportion. The size of the lumber has more resistance as it gets smaller. And I found that really amazing, okay? Really amazing. But like I said, you don't have to worry about this. This is already incorporated in the table, but you know, size is a factor when it comes to wood, okay? So keep that in mind. And like I said, so now KL is a lateral stability factor, like I said, okay? The table values are based on joists that are restrained against lateral displacement. What that means is that if, okay, here's my joist, okay, it's spanning this way, okay? Now, when a joist is being loaded, okay, when a joist is being loaded, because the top is in compression, it can start swaying out of its thing. So therefore, you have to make sure that the joist is laterally supported. And then steel, we'll talk about lateral supporting, okay? The tables are based on, are against displacement and rotations at the end. So in other words, here I have a header joist. I'm going to nail here. I have a header joist. So I make sure that everything stays relatively in place when the load is being applied, and therefore the thing is relatively stable. Okay. The compressive edge are held in line by sheeting. Okay. So normally, of course, the thing is simply supported. We know that this is the compression side. We know that we always put the plywood on the top. So therefore, okay. And the bridging is provided at intervals not exceeding 8 times the member depth. So people have always asked me, it's like, for example, when I have joists, okay, when I have joists like this, okay, when do I start putting some cross bridging in between? Well, if I'm using 2 by 10, okay, so in other words, if the span happens to be more than 8 times this, if the span happens to be more than 80 inches, then I should put a row of cross bridging, and that's what they're saying here. So just if you want to remember this, the interval for cross bridging is 8 times the member depth. So if I'm using 2 by 12s, 8 times 12 is 96. So any span over over 8 feet, I should be applying a row of cross bridging. And if I happen to, so in other words, it's 8 times the member depth is when you should be putting the cross bridging to provide a lot of stability. You can either put cross bridging, you could put blocking, whatever, okay? And then if this is what you do, so like when you're building a floor, you know you're going to be putting sheeting down, you're going to have some, some header joists that are going to be holding the joist into place. It's going to, so all of this is going to be met, so therefore you don't have to worry about it. Your KL is 1. But if ever you have a piece of wood all by itself here, okay, let me show you, okay. Like for example, if I take a piece of wood here, okay, all by itself, and I'm supporting it there, and I'm supporting it there, and there's nothing on top, and I decide to hang something here, okay, and I calculate the MR based on this load here, P, okay, well, I cannot go to the tables because my KL is not equal to 1.0, and therefore I would be absolutely wrong, okay, so that's what they're saying. If the member is not laterally supported, don't use the tables. Okay, and if you do happen to get into that situation where you have one member by itself, nothing's laterally supporting it, well, I can show you what you have to do. The table tells you how much you have to diminish the values by because of the instability of the member. So keep that in mind. I like to stress this, and I will talk about unbraced length in steel more. You'll be able to relate this more. So this is KL, okay? And like I said, the table is based on the fact that the value of KL is 1. So you can see that the table has a value of KD standard 1.0, KS dry 1.0, KT untreated 1.0, KL stable 1.0. So everything in the table is 1.0. Now, any other condition other than standard, dry, untreated, unstable, you have to modify the values in the table. And that's what these values are for, okay? Now, let's talk about bearing, okay? Bearing is where the member sits on its reaction area. Now, this here, of course, is called a hanger. Now, even though it's a beam, okay, this is a hanger, okay? And these are beam hangers. You can have joist hangers. So this is one type of bearing. So bearing is where the piece of wood is resting on its reaction area, okay? Now, the reaction area can be a hanger, it can be a plate, it can be whatever, okay? So this here is the bearing length, LB, okay? So bearing resistance. Now, what you want to do is you want to make sure that this is long enough so when the load gets transferred from the member into its reaction area, you definitely don't want to have this happening, that the fibers start crushing here, okay? And all of a sudden you end up with a member that starts to look like this. And so in other words, the members have all crushed where it's sitting and the thing starts to settle. And of course, when things start to settle, people complain because things start to crack. So the LB guarantees you that the fibers that are parallel to the lumber will not crush under the load that's being transferred from the joist to its reaction area. And I say reaction area because you can have a joist hanger, you can have a sill plate, you can have a wall, whatever it is, okay? So that's what bearing is. Okay, so in other words, from here to here, this is what they call the LB, the bearing length, okay? And you'd have to calculate what is the minimum length you need in order for all the fibers right sitting on top of this hanger that they don't crush of the load that's being transferred from the beam to that hanger.
Sir?
Yes.
So if you make it longer,
it's perfect. This we'll calculate the minimum and make sure that if you're providing more than the minimum, then you're okay. 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 So in other words, if you make it longer, all the better. You understand? We're going to calculate what is going to be the minimum. So for example, if I'm sort of like, if I calculate here, I'll give you an example. I have a joist here, and I calculate here that the LB required, okay, LB required, let's say I do my calculation, LB required is 24 millimeters, okay? Let's just, that's what I need, okay? And all of a sudden, I know I'm gonna be sitting on a 2x4 wall, and I know that this here is 38 millimeters. Am I, or not 38 millimeters, this is 89 millimeters, a 2x4 wall. So am I okay? Yes. In other words, I need 24 and I'm providing 89. So therefore, absolutely no problem. The problem would be is that all of a sudden I have my wall here, okay? I have my wall here, and the carpenter decides to just sit it there for because this piece is not long enough, and all of a sudden I have an LB of 20 millimeters. Is that good enough? No, because I need 24. You see? So if you provide more than is required, perfect. If it happens to be less than what's required, you've got a problem. Okay? So that's why. So don't worry about providing more. Worry about if it's less. Okay, so here is for the bearing under the effects of all factor loads. Okay, this is the general. Okay, QR. This is what we saw before. The bearing resistance QR has to be greater than the compressive force QF. Okay, now QF, depending on the situation, is just the loads that are being transferred perpendicular to the fibers. And of course, if it's just one member by itself, then the QF is the VF and so on. Okay. Now, here is QR. QR is a small QR value times your LB, which is a required length. So QR is the factor compressive resistance perpendicular to the grain. Okay. Now, guys, I should mention this. I take this for granted. Okay. Remember, wood has, I don't know if you've ever seen it, but wood has a certain grain in it. Does everybody know that? Or you guys never noticed that in wood?
I know that.
Okay, so one thing you should note is that wood has a certain grain, okay? So here, if the force is being applied, okay, in this direction, the wood has one resistance. When the force is being applied in this direction, the wood has another resistance. So here, okay, this is when we say the force is being parallel to the grain, and this is when the force is being perpendicular to the grain. Okay, so this is parallel to, and when we're talking about bearing, we're talking about, okay, the resistance when it's perpendicular to the grain, because it's going through where the fibers are being perpendicular to it. So this is why they're saying the factor resistance perpendicular to the grain per millimeter, okay? And we're gonna get the value from the table. So I always assume you guys know that there's a certain direction to the grain, and therefore, you know, when we're talking about parallel or perpendicular, but I might as well repeat it. Okay, now, so here's the equation, big QR, and of course the big QR has to be greater than the big QF and all that, and this is, okay. Now, here's a table, very simple, okay. We do not use this, we do not use this, we do not use this. So therefore, depending on the thickness of the lumber, in other words, if my lumber here is a 2 by whatever, in other words, 38 millimeters by whatever height I want, okay? It doesn't matter how high it is, okay? Okay, the amount of resistance here that I have per millimeter, okay? So in other words, the amount of resistance that I have is so many kilonewtons per millimeter. So that means that as long as it's a 38, I don't care if it's an 89, a 140, or a 180, or 235, or 285. I don't care if it's a 2x4, 2x6, 2x8, 2x10, 2x12. That doesn't matter. It's this length, it's this width that's important. It's a 38. For every millimeter that it sits on its bearing area, for every millimeter that it sits, it has a resistance of so many kilonewtons. So therefore, the QR value is going to be equal to 0.161 kilonewtons per millimeter. So if I set just 1 millimeter on this edge, it's going to have a resistance of 1.0161 kilonewtons. If I put 2, it's going to be twice that, 3, and so on and so on, okay? So this is the small QR value that we get straight from the table. And therefore, what we'll do is based on this value here and based on the QF value that we have to design for, we'll be able to calculate what the LB is, and then we've basically done our calculations, and you'll see that in an example. So that's what this table is all about. So like I said, this value here, I will be using it throughout the whole semester, okay? Now, of course, if you have 48, if you have 89, if you have 114, okay? And surprisingly enough, if you take this and you take this ratio here, this should be the same as that value for that thickness, and the same as that value in other words. So this is just, as far as I'm concerned, I just need to know one, and then if I know for 38 is so much, I can not without having to come back to the table, I know what these values are. So, but like I said, the one that I use constantly in this course, this one here, because most all the lumber that we're going to be using for the joists and so on are all going to have a thickness of 38 millimeters. It's going to be a 2 by something. So therefore, I know my QR value is going to be 0.616 for this small QR value in my equation. Now, here what it says that the QR value does not vary with grade. So it doesn't matter whether you're using select structural, doesn't matter whether you're using number 1, number 2, number 3 stud grade, or whatever, the QR value will not vary with the grade of the wood. It varies with the species, but not the grade. So regardless of the grade, the QR value stays the same, okay? That's why we don't have a table for species and grades, and we just have the species. We don't have the grade. Okay, now here is, I love this. So even for this little table, the handbook has a checklist, okay? So to verify the tabulated value QR in Q, okay, phi FB, okay, the values of the, okay. Now, is a low duration standard? In other words, is KD equal to 1? Yes. Is the service condition perpendicular to the grain? That's why they have this perpendicular to the grain, SC, okay? Dry, yes, so 1, okay? Is the material free of incision, okay? And, or is KT 1, yes, okay. Is the bearing area of the member, okay, in high bending stresses, okay? The answer is no. In other words, if you look at your member here, okay, it's like if this is your floor joist, and if it's sitting here, and if it's sitting there, well, if this is the bending, right? I'm sorry, yeah, that's the bending. So what's the bending stress at the reaction area? It's 0. So therefore, we are not in a high, okay? Is the bearing area at the end of the member in a high bending stress? Okay. The answer, okay. And of course, is a member, okay, less than or equal to 1. So in other words, if you happen to have like a 2 by 4 or a 2 by 8, like when you're putting the wood like this, the bearing resistance here has one value, but if I take the same wood and turn it like this, for the same wood, because this is wider than this, for the same species, that helps to increase the bearing resistance. And that's what this is all about, okay? So the same thing as the joist tables, there are factors also for these values here in these tables. So they're saying, is KD equal to 1? Is KS equal to 1? Is KT equal to 1? Yes, yes, yes. Go use the value in the table. Okay?
Sir,
Yes.
for number 4,
Yeah.
so how can it be like high in an area high bend? Yeah. So how can you put the edge when it's not supported at the end?
When it's in cantilever. Don't you have a high bending stress for the cantilever?
Yes, yes. Okay, I figured. Okay.
Okay. So, and you know, so in other words, that's what you have to worry about. Okay. So is the bearing area at the end of the member in a, okay, or in an area of high bending stresses, okay? Oh, I'm sorry, is the bearing, okay, is the bearing area at the end, in other words, is it in, okay, what they're saying is that, exactly, is the bearing area at the end of the member? So like when you have a member here like this, sorry, I should have just said it more simple. This is at the end of the member, yes. Yes, okay, so therefore, you know that you said yes to this. In other words, that's what you're calculating the bearing to, okay? Or in an area of high bending stresses. In other words, are you loading the member here? The answer, no, you're not, that's not what you're checking. You're just checking the bearing here. So the answer is yes, okay, and so on. Now, okay. Now here, so here, for example, KT, KD, okay, for this table here, it's the same values that we saw for the joist. In other words, K for short term is 1.15, for long term is 0.65, for standard is 1. So the KD value stays the same whether you're doing for bearing. The KS is different though, okay? The KS is 0.67, okay? And I want to stress this. So this is the KS value. Now, it doesn't matter. You're not looking at shear. You're not looking at bending. It's just perpendicular to the grain. The KS value is 0.67. So you have to change the value for KS when you're doing the bearing. And the KT values, okay? Here, 0.67 for dry. Here for wet. And this is for solid number greater than 89, which we're not going to be using. So therefore, we're not even going to be worrying about this, okay? So since we're going to be using 89 or less, okay, this is the values for KT. Okay, so if it's KT is dry, then it's 0.75, KT wet, 0.85. And this is just for bearing. And we're going to be applying these in one of the examples, so don't worry about it. Now, there are other situations. If you want to take advantage of factors that will actually increase your bearing, you can. If you want to disregard them, don't worry about it. You're just going to be safer, okay? So in my case, I don't even bother, but I'm just like, here what they're trying to show you is that if you're calculating the bearing, okay, if you're calculating the bearing here, okay, if you're calculating the bearing here, okay, what they're saying is that for P1, R1, R2, in other words, P1 here, R1, R2, there's nothing to take advantage of. It's just the KB value is 1.0. For P2 in areas of high bending stress, doesn't matter. The only time it becomes, you can maybe take advantage of this KB factor is when you're having a bearing wall sitting greater than 75 millimeters away from the reaction area. If you want, you can increase your values of bearing, but if you disregard it, don't worry, it won't hurt you because you're being more conservative. And this here is, for example, the size factor, which if you don't have to worry about it because this is already incorporated in one of the tables we're going to be using. But for example, if I put my piece of wood like this, okay, in other words, the size, okay, the tabulated, okay, is it 1 or less, okay? The size factor, it reflects the width to member ratio, okay? Width, what is it? To depth ratio, okay? So in other words, if this ratio, if W is equal to D, then you use 1. If D is greater than W, you use 1. It's only when D is greater than W, in other words, when you take a piece of wood and you put it flat like this, okay, so here, this becomes your D, this becomes your W, and therefore you can actually increase the resistance by 15%. And don't worry about that. Where we're going to have the situation, this will already be incorporated in the table, so they've already taken advantage of that. So I'm just showing you the other factors that you can use 1 or something greater. So if you disregard this table when you're doing your calculation, you're only being more conservative. It won't hurt you. So that's why I don't stress this very much, because I only stress things that if you overlook, it can hurt you. Here, if you overlook these factors, they won't hurt you. They're only going to be adding or being beneficial to your end design, okay? So if you forget to add these in. Okay, now, here's an example. Here, how are we doing time-wise, guys? I'm sorry.
Oh, we still have 1 hour and a half left.
4:30?
Yeah.
Oh, okay.
Until 6.
We're doing great. Okay, so guys, now that we went through all that theory and I filled up your minds with all this wood stuff, and I hope you're smoking because wood does burn. Here, we'll apply this to an example, okay? Design the floor joist for the following conditions. So here we have a joist spacing, okay? Now, here I'm giving it to you, but normally, guys, you would have to decide on a spacing. So if it's on the floor, I would start with 400, and then if that didn't work, I would go down to 300. You understand? I would start, but I wouldn't go start with 600, go to 400, go down to 300 for a floor. I would start at 400, 16 inches, and if that doesn't work, I would change my spacing to 12 inches, and if that doesn't work, well, then I'd look at doing something else. So here I have my spacing of my joists. In other words, I'm going to be putting them parallel to each other at every 16 inches on part, okay, on center. And the span, in other words, it's supported, either can be on 2 beams, or it can be on 2 walls, or it can be on a beam on a wall. The span is 3 meters, okay? So there's my span. Now, here's my dead load, which was simple. It's given to you, but you know, in reality, you always have to calculate your dead load. And of course, here's my service load of 2.4 kPa. So this can be a floor that you're going to be installing in an office building, in a classroom, wherever, because that's the typical live load for that kind of an occupancy. And you have standard load duration. In other words, it's just going to be, you know, a live load on your floor with the typical dead load. So your KD is equal to 1. Of course, you're doing this inside of a building, and it's hopefully the envelope's going to keep everything nice and dry. So your KS is equal to 1, and you're not going to use any treated wood because you don't have to treat it, because it's not going to be subjected to possible, you know, rotting because of the environment that it's in. So we're going to use untreated wood. So that's nice. KT is equal to 1. Now, fully laterally supported by the subfloor, which is nice, of course. In other words, you're going to have some sheeting over your floor joist, and that's going to be fastened. And not only are they going to be fully laterally supported, that means your KL value is 1. Going to have a case 2 system. That means when I'm going to go to the tables, I'm looking for the values of resistance, MR, VR, ESI. I'll be able to take, well, the ESI doesn't matter whether it's single member, case 1 or case 2, they are all the same value. But for the MR and the VR value, it's going to have an effect on the value. And the joist supporting finishes susceptible to cracking. So what that means is that I have a floor joist here. I have another one there, okay. I have another one there. So they decided to put some nice plywood here, okay, that's going to stabilize everything. And right here, I'm going to have, a piece of gypsum board attached to the underside of my ceiling. And since gypsum is susceptible to cracking, I have to make sure that when this member is going to deflect, the gypsum board that's attached to it does not start cracking, okay? So that's what the serviceability comes in, okay? So we're gonna have to check that. And we're gonna use SPF number 1, number 2 lumber, and I'll always be using for bending, always gonna be using SPF number 1, number 2 lumbers, okay? Now, in this case, we don't have to worry about our geometry. It's been given to us. We don't have to worry about calculating our loads. It's been given to us. So the only thing that we have to now do is change our specified loads into design loads. And how do we do that? It's by always factoring our specified loads. Okay, so case 1 combination, we have 1.4D. Okay, and for case 2, of course, is 1.25D. That's where, okay, when you add your dead load with a variable load, the load factor goes from 1.4 down to 1.25. And of course, this is the load factor for your occupancy load, and therefore you always design for the higher of the two, because if I design for this value here, I'll automatically have compensated for that. Now, how do I, so in other words, how do I get, this is, you know, I want you guys, please, I take this for granted, but okay. So here is my floor in plan view, okay. Here's my floor in plan view. I have these joists going across the floor at every, whatever, 400, okay. And now all of a sudden I've got loads here, okay, for every square meter, which is about, okay, for every square meter here, I have a dead load. For every square meter, I have a dead load of 1.5 kilonewtons. And for every square meter, I have a load that's being applied over the surface area of 2.4, okay, kilonewtons. So that's the pressure, or that's, you understand, that's the pressure that's being applied to these members. And of course, when I want to design a member, I have to be able to calculate In other words, when I want to do my analysis, this is my span L. I want to be able to get a uniformly distributed load here. In other words, the units for a uniformly distributed load is kilonewtons per meter. And that's what I need here. And that's what I need here. So how do I go from kilonewtons per meter squared? How do I go to kilonewtons per meter? Well, I look at the tributary width that each member is carrying. Okay, so this is the tributary width that each member is carrying. So I take my factored load and I multiply it by the tributary width, and that will convert everything into kilonewtons per meter. Okay, and of course, when you have members that are equally spaced, okay, you just take the spacing of the members if they're all equally spaced, and that becomes your tributary width. Is that okay with everybody? Is that clear?
Yes, sir.
Okay.
Yes, sir.
Sounds good. And so that's why, like, okay, so WF, and you'll notice that, okay, let me clear this drawing. Okay, so here, why do I put F here? That means my loads have been factored. Okay, that means I'm using my design loads now, no longer my service loads or my specified loads. And I put this substitute F, so I know that I'm using my design loads. So here I take the tributary width is a joist spacing, like I just showed you. Okay, so therefore I take 5.48, my factored load, times my tributary width, my joist spacing. I go from kilonewtons per meter squared times 4 meters. I go down to 2.19 kilonewtons per meter. So that's my WF. Okay, from this, of course, I can now calculate the total specified load. Okay, because this is for serviceability now. Okay, and of course, when using the total load, that's L over 180. So therefore, you take 1.5 plus 2.4, you add them both together, and you multiply it by 0.4. And that's W for serviceability for the total load. And then I have another one just for the live load, because the deflection criteria just for the live load is different than for the total load, because the total load is L over 180. The live load is L over 360. So therefore, I have to calculate a WL just for the live load. And therefore, I end up getting 0.96. Now, people say, wow, what happens here? Well, this deflection criteria here for this one, for the total load, is L over 180. And the deflection criteria for just the live load is L over 360. So in other words, this one takes only half the deflection of this one, and therefore that's why you check both, okay? And of course, this one's required by the standard, and this one, of course, is required by the National Building Code. So they're both required, although this one's suggested in the standard. Okay, so now I've got I have my 3 loads that I can use for my analysis. And now I can go ahead and, of course, perform some simple analysis because everything is simply supported. I know that MF is equal to WF L squared over 8. You should remember this from your beam load diagrams, that when I have a member that is simply supported with a uniformly distributed load across the whole member, that the maximum moment occurs at the center, and the maximum moment, MF max, is the load WF here, times the span, L squared over 8, and that you get from your beam formulas, okay? And of course, we did this quite a bit last year, and this year you're gonna get saturated with WF L squared over 8 between the steel and the wood. And then after that, I calculate my MF, and then I want to calculate my VF. And of course, the maximum shear occurs at the reaction area, which is equal to WL over 2. And of course, the units are in kilonewton. And then I need to calculate the ES required, okay? So when I'm talking about the total load, the deflection criteria is L over 180. And this is the deflection equation for A. In other words, this is delta is equal to 5WL over 4, 384 ESI. This is the equation to calculate the deflection caused by a uniformly distributed load. And I don't care whether it's, and of course, this is what governs the deflection criteria for the total load, L over 180. And then for the live load, well, it becomes L over 360. And it's exactly the same equation, okay? Except this is total load, this is just a live load. And it's just specified total load, specified live load. And these are factor loads up here. And of course, I put ESI because that's what I'm going to go look in the table. So I put everything in terms of ESI. And people say, well, how come I went to L cubed? Well, this L here cancels this and brings this down to a cube. Okay, and of course, the 180 from here goes up there. The L goes down here, so this becomes cubed. So ESI requires 180 times 5 times W times L to the fourth, and then the ESI for the live load, and that's how I differentiate these two, because this is total load and this is the live load, and this is the equation for the live load. Now that I've got all my equations, I can go ahead and do the calculations, okay? So if I take this I end up getting 97.8 times 10 to the ninth. And if you look at the units, guys, it works out, okay? Newtons, and of course, I'm sorry, hold on, let me clear the drawing. Okay, if you look at it, okay, so the newtons don't cancel. This cancels by this, and therefore I get newtons per Newton millimeter squared, and that's the value that you see in the tables for the stiffness of the beam. So you work, and guys, remember, use a scientific notation times 10 to the ninth. In other words, whatever answer you get from this, okay, just divide it by 1,000 cubed. Or if you want, that's how I do it. I just take the value in the table and divide it by 1,000 cubed, and I get it 10 to the ninth. So remember, use a scientific notation 10 to the ninth. Otherwise, you won't be able to go find the values in the table. Okay, and that's the easiest way I do it. Now, so right now I've got my I've got my MF, I got my VF, I got my ESI required, the one that governs. And of course, now that I got my three design forces, and they're, I can go ahead and of course I can go straight to the table because I know KD is 1, KS is 1, KT is 1, KL is 1, everything is 1. So I'm allowed to go straight to the table and pick my member, okay? Now, guys, when I come to the tables, the first thing I look for is my MR value to make sure it's greater than my MF value, okay? So the design objective MR greater than MF, VF, VR greater, and then the ESI provided greater than the ESI required. So what I do is I come here and I say, so do I have a single member? No. I know I have a system 2, a system case 2, because I have a subfloor, nailing, everything, at least 3 members, blah, blah, blah. So I start looking for an MR value that is greater than 2.46. So I go down. Okay, so here's my MR value that's greater than 2.46. So that's good. Now, is my VR value greater than my VF value? So I have a VF value of 3.28. I have 10.1. Yeah, that's good. Is my ESI provided times 10 to the ninth greater than the ESI required? 187. I need 121. Yes. So that means that my deflection will not exceed 360. In other words, it will not exceed the deflection criteria required, the minimum deflection criteria under live loads. So therefore, I know that a 38 by 184, which is basically a 2 by 8 inch piece of lumber, would be sufficient to support the floor load, okay? And therefore, now, guys, what you're going to see next is the way I want you to show it anywhere, whether I ask for it on a test, whether it's for the project, whatever it is, okay? This is how you have to show the results of your choices. In other words, you're going to say, you always write the species that you chose, you always put the grade that you chose, and you always put the size of lumber that you chose. So in other words, species, grade, and size. So in other words, when if I give you this on a test to do, if you don't put down SPF and you don't put number 1, number 2, and you don't give me the size, I will mark it wrong.
Sir,
okay? Yes.
So you said just now that the system case number 2, MR and VR, has to be greater than your MF and VF.
Well, that's the design objective. Our design objective is always MR
So
greater than or equal to MF.
So my
Okay.
question is, how
Yes.
come we chose the 38 by 184 if the 38 by 140 would theoretically work?
It does?
Yeah, because that's 2.58 for MR and 9.38 for VR.
And what
Yeah,
about
but your
oh,
ESI
It doesn't.
is too big after.
and
Sorry?
what happens to the ESI value? Is this greater than 121.5?
Okay, that's the one I didn't see. All right,
See, you
I
have to
get it.
you have to make sure that the three criteria are satisfied. Sometimes it's strength, sometimes it's stiffness. So in this case here,
Okay.
Nicola, this in other words, what they're saying here is that this gives you ample strength for the loads you're going to be putting on your floor. Don't worry about it; it's not going to break on you. But what's going to happen is that, like this one's going to give you ample strength, but you're going to have a problem with your deflection.
Yeah, got
So
it.
it's good for strength, no good for serviceability. Okay, fair enough. Yeah.
So if we didn't have gyprock, would it be fine?
Oh yeah, because then if we had no gyprock, this is what we would need, right? No, we still wouldn't be fine. Because look, this is what we need with no gyprock. Will we still be fine? No. You understand? And that's why you have to check. Okay. So even there, if there's no gypsum, because the minimum deflection is L over 180, sorry, it don't work. You follow? So therefore you have no choice but to go for this. So in this case here, believe it or not, it's not strength that governs your design. Guess what it is? It's serviceability. It's the stiffness. It's no longer just the strength. And by having the serviceability, it has more than ample, you understand? So even under no gypsum, it wouldn't work because this here, 98.7, 82.5, still no bid, okay? So I'm glad you guys are starting to relate to this, okay? So this is why all three criteria have to be met, okay? And I'm sorry, I jumped right away to that one because I saw this number at the corner of my eye, so that's why I went to that one. But I should have started with this one and shown that this is no good because of this, and then I have to go to the next one, you understand? I should have done that. Sorry about that. And like I said, I only took the part of the table that concerns us, okay? I mean, the headings are all the same in the tables and all that. Okay, so this is what I want to see. I want you to tell me this is the species you're using, this is the grade you're using, this is the size that you chose, because this way somebody that's checking your calculations, if they want to go back, they can go back to the table and see, yeah, let's see if he took the right values, you understand? Because sometimes you can make a mistake. You can come to the table and all of a sudden you're looking at these values, okay? You're looking at these values and you're picking something wrong. So if somebody's checking your answer, he wants to make sure that you can go back and double check that you've done everything correctly. So that's what I want to see. And on top of that, so I want to see, so therefore, and then I want you to write MR, the value you got from the table for MR, and show that it's greater than your MF value. VR, which is what you got from the table, is greater than your VF value, and that the ESI provided that you got from the table here is greater than the ESI required. Now, you've designed the member for it to be able to stay in, you know, to support whatever it is that has support. Now, the next thing you have to check, of course, is the bearing length, okay? So the design objective is always QR should be equal to QF. Now, what is QF? QF is a force that is perpendicular to the grain. So if I look at my piece of wood here, okay, the force that is perpendicular to the grain is my VF force. So therefore, in this case here, QF is going to be my VF force. So that's what I have to look at. So QF is equal to VF because that's the force that's perpendicular to the grain. So I have to design for this force here. And I know that my QR is equal to my small QR times LB greater than my QF value. That's my design objective. And therefore, I know my QR value from this table here. I know I'm using a 38. That's the width of the lumber. I'm using 38. And I know I'm using SPF. Therefore, the small QR value is 0.161 kilonewtons per millimeter. And that's what I get from the table. And therefore, I end up getting small QR is 0.161 kilonewtons per millimeter. And therefore, now I just go the LB required. I just do the calculation. I end up with 20.4 millimeters. So this means, and guys, don't go over one decimal place when it comes to bearing. It's ridiculous. Okay, you're talking millimeters here. We're not talking inches. Okay, we're talking millimeters. So that means that as long as my piece of wood is sitting on something here, whatever the reaction area here, as long as the L here, the L be provided, okay, the L be provided is greater than 20.4 millimeters, I'm okay. That's what it means. So therefore, you just got to make sure that this thing is sitting on something that has at least, so for example, if I decide to put a joist hanger, everybody knows what a joist hanger is, okay? I got to make sure that the seat of the joist hanger here that the manufacturer is providing has at least 20.4 millimeters of length for it to be okay. If it doesn't, I can't use that joist hanger. That's what it means, okay? And in most cases, these joist hangers have sufficient length here for the joist to be able to sit here and rest properly on its bearing area. Okay, so, and that's it. Now, okay, again, I just don't want to 4:30. Oh yeah, we got time. Okay, so now, so that was one example where KD1, KT1, KS1, everything is one, straight to the tables, and let's go and get our values. Now, let's do one where design the floor joist of a warehouse storing moist materials. Great, okay, I've got moist materials now. And I'm in a warehouse. Now the joist spacing is 300 in this case, and the span is 2.4 meters. This is the geometry that I worked out based on what the architect gave me to be able to work out my structure, okay? So I've decided to put my joist spacing at 300, and I decided to put in the span, I've decided to create spans that are 2.4 meters long. Here's my dead load of 1.0 kPa. Here's my live load of 4.8 kPa, which is a, substantial, 100 pounds per square foot for a warehouse is not too bad. And fully lateral is present. So therefore I have a case 2 system. I can still use a case 2 system for the MR value because it's fully lateral supported by floor, case 2 system. In other words, I'm going to make sure that it's nailed properly to my sheeting. Joist not supporting finishes susceptible to cracking. Oh, great. I don't have to worry about L over 360. I only have to worry about the total load, L over 180, because there's no materials, but I still have to maintain that minimum stiffness required by the standard. And of course, I like to use SPF number 1, number 2 lumber, because that's the only thing we're going to be using in Quebec, as far as I'm concerned. So now, step 1, factored loads. Well, same as before. We have a case 1. I'm sorry, I should put combination 1. I should change this to combination 1. Okay, just a dead load, or combination 2 where I have the dead load combined with the live load, and therefore out of these two, this one governs. And of course, WF, as I explained before, is your factor load times your tributary width. And the tributary width, when you have joists equally spaced, it's always the spacing of your joist that determines the tributary width, as I explained before. So the tributary width is a joist spacing here. And therefore, I go from kilonewtons per meter squared down to kilonewtons meter by multiplying it by the tributary width here. So I go down from, this is what the member is carrying. And of course, I don't have to, and I got to calculate my W, which is the total specified load times the tributary width. And therefore, I add the 1, and I don't factor the 1 to the 4.9. These are all unfactored loads, they're just specified loads multiplied by my tributary width. So that becomes my W. And in this case, I don't have to worry about WL. I don't have any material susceptible to cracking. So MF, WF, L squared over 8. Here's my MF value. VF, WF, L over 2. Here's my VF value. And of course, ESI required 180 because it's the total load instead of the 365 WL cubed over 384. You saw from the previous example how I was able to derive this based on, L over 180 is equal to 5 WL to the 4th over EIS. And of course, now I calculate the ESI required, okay? And like I said, make sure you have the scientific notation of 10 to the 9th, otherwise you won't be able to go to the tables. And of course, the easiest thing I do is I take my value divided by 1000 cubed, and I get 10 to the 9th. Now I've got my MF value, I got my VF value, and I got my ESY. But the problem is that if I go to my checklist, do I have a standard load? No, because it's a warehouse, things can sit there for months on end, so therefore my KD is no longer 1. Am I in a dry condition? No. So my KS is no longer 1, okay? am I going to be using treated wood? Most likely, because I'm in a very moist condition. I might want to use some treated wood. So my KT is no longer equal to 1. Okay, so now what do I do? Okay, now of course, okay, so the design objective is that since my KD is not equal to 1, my KSB is not equal to 1, my KT is not equal to 1, I have to take the values in the table and multiply them by all these factors in order to determine my MR. And then I got to make sure that that MR value is greater than the MF value that I just calculated. So that's what I have to do. Because the table is based on 1, 1, 1. I no longer have 1, no longer have 1, no longer have 1. And the same thing goes for the shear. I take the KD for the shear, the KVS for the shear, the KT for the shear, take the value in the table, multiply by these three, and I have to make sure that that value in the table is greater than the VF value that I've just calculated for my analysis. And the same thing for the bending. The KSE for the service and the KT for the treatment for the ES provided, I have to take those two factors, multiply the values in the table, and make sure it's greater than that. Now, I can go straight to the table, okay, and of course, okay, so here's the modification factor. So if I go back, okay, so I know that I have a long-term load. I'm in a warehouse, so therefore I should take a KD equal to 0.65, okay. So there's my KD value. And then as far as the bending, SB is 0.84, for the shear is 0.94, for the serviceability is 0.94 here. And, okay, for the treatment factor, okay, if it's wet, if it's dry, it's 0.75. If it's wet, it's 0.85. I'm going to be wet, so this is the KT factor. And here's the KT for the ESI value of 0.95. So here are all my factors that I have to go to the table and multiply by and make sure that the MR, VR, ESI provided is greater than what I need. Okay, so here, so therefore, instead of taking the values in the table and multiplying them by these factors, I like to take my force and divide the factors. Okay, and the reason why I like to do this is that I will then be able to go straight to my table and compare the value in the table to what I have here. And that's the smartest way to do it. Now, you don't see this in the handbook. This is just common sense me that has determined to do it this way. So therefore, I will replace this by 0.65, KSB by 0.84, KT by 0.85. I will put all the factors on this side, which will modify this. And then I can go straight to the table and find to make sure that this value is greater than whatever value I have on this side of the equation. Okay, so that's the easiest way to do it. And I do the same thing for VR. Okay, I take the KD. The KD stays the same whether it's for K for the shear. Okay, it's 0.65. This, of course, is different for shear. This was 0.84. This was 0.8, and this stays the same. So therefore, that stays the same. And I'll do the same thing for the ESI. So this is for the service and for the treatment, and therefore I will modify this. You notice that KD does not come into effect when it comes to bending. Okay. Now, so I do this. Now my MR value is no longer has to be greater than 1.83. My MR value has to be greater than 9.94. So now I can look at the table and find an MR value that's going to be greater than 9.94. And I know that when I take this value and I plug it back in here and I multiply by all these factors, it's going to give me the satisfy this condition. And the same thing happens for VR, 0.83. And I have, so now I'm looking for a VR value that's at least 5.75 in the table. And the same thing happens for the stiffness, okay? And that is the easiest way to use the table, by amplifying or modifying your force so that you can go straight to the table. And therefore I have now, this ends up, so now that I've got the values that I can see straight from the tables, in other words, I can look for an MR value in the table that's greater than that, a VR value that's greater than that, and an ESI that's greater than that. I know that if I meet these three conditions, when I take the values in the table and I stick them in here and I multiply them with these factors, I will always get something greater than that, and greater than that, okay? Clear all drawings. So now I go to the table and I start looking. So like I said, when I come to the table, I like SPF number 1, number 2, that's the species, okay? So I have a case 2 system, Okay, so like I said, I like to always start with my MR value. So I'm looking for an MR value that is greater than 3.94. So 3.84, that's no good. So here's greater than 3.94. So therefore I'm looking at least this. Then I check the MR value against the VR value against, so I need a VR value greater than 5.75. I got 12.4, that's good. And I look at the stiffness, I need 63.2 and I got 390. Okay, so then this is a good choice. Anything before this. So in other words, if I would have come to the table and said, well, let me try a 2x8, and all of a sudden I put it in here, you would have ended up getting something less than this. It wouldn't have worked. That's why I like to modify the values and then be able to go straight to the table. So from here, now, so therefore SPF number 1, number 2, 38 by, so in other words, a 2x10. Okay, guys, I'm gonna tell you these in imperial so you guys can start getting used to it. 38 by 235, because when you go to the lumberyard, it says I need a 38 by 235. He won't know what the hell you're talking about. If you tell him I want a 2x10, he'll know exactly what you're talking about. So this is a 2x10. So the MR value of 5.72 is greater than 9, which is great because I can actually take this value now and multiply by all these factors, and it would still be greater than 1.83 here. And I take the VR value, which is greater than what I have here, and I can take my ESI provided and be greater than I have here, okay? Now, that's just for the member carrying the load. Now, of course, you have to do the same thing for a bearing. And again, now, guys, don't make the mistake, okay? I've seen this, the classic mistake is that people take this VF value here, okay? They take this VF value here when it's been modified, I'm sorry. And then they use this for, they take this value here and they go calculate the LB. That is wrong because the modification factors for bearing are not the same as the ones for bending and for shear. So don't make that mistake. Do what you're supposed to do. You know that your VF value is 305. That's what you calculated from your analysis. And you know that this is your objective, that the QR, which is a small QRLB, has to be greater than that. But you know that, okay, you have KD, which is the same values as you had before, but this is different. The service in compression perpendicular to the grain, okay, is different than the ones that you had before. So that's going to be different. KT can be different. So therefore don't, okay. And of course, these three values multiplied together and your small QR should give you the LB required. So therefore the LB required is your QF here of 307 divided by all these values here. Now, if you come to the table, KD, same as before, 0.65. Now, the KSC is now 0.67. That's where you find this here. So the KD for permanent or long-term, I should say, long-term is 0.65. The service one is 0.67. And for wet is 0.85. Okay, so therefore, that's where I get my KT value for wet. If it was dry, it would have been different. And therefore, so now I put in this value here, it will modify the LB required, and now the LB required becomes 51.2. So as long as the member sits at least 51.2 millimeters on in its at where it's being supported, you know you won't have a problem in bearing. And I think that's it. And now I've prepared, well, I'm going to be sending you an assignment through Leah. It's supposed to be delivered around 5:30 or 5 o'clock or whatever.
Oh, we already got it.
Okay.
Yeah, I just received it.
Yeah.
Okay, exactly. So I'm using Leah for almost everything now. So you've already got it. I strongly suggest you do the assignment, right? Because it prepares you for the test. And of course, I always do the solution to the assignment first thing in the next lecture. Okay. And I guess that's it. Now, hold on before we go. Oh yeah, that's exactly. Okay. So guys, this is your first, I mean, I know there's a lot to take in. Don't worry, we're going to be going over this again next week, and all these factors are going to be applying when we do the beams and so on. So the factors, you're going to start getting familiar. And unfortunately, that's one of the drawbacks with wood design. Well, not the drawbacks, that's one of the things that you're going to have to get used to. Wood is a very natural product, and therefore, since it can be affected, you know, by excuse me, since it can be, I'm going to take a sip of water, excuse me. Since it can be affected by the duration of the load, this can be affected by the environment that it's going to be sitting in, since it can be affected by the chemicals that are going to be used that are going to help to treat the wood and, you know, increases durability and so on. These factors have to be taken into account, and that's one of the, you know, things that, like for me, of course, it's very simple. I've been designing and I've been teaching this course for it, so I know these fairly well. But don't worry, you'll see it becomes quite repetitive, and you'll start getting familiar with them. And you, like I said, you don't have to memorize them. You just have to be aware of them. And when you come across them, where can you find the values and where you should be applying? That's what I'm trying to stress here. So now, okay. Oh, sorry.
Sir, I have a question. Could you go back a few slides? I didn't see the last part of the what you did there.
Here?
Yeah.
Well, what I did here is that the values in these tables here, okay, are all based on a standard load, dry service condition, untreated wood. In other words, KD is 1, KS is 1, KT is 1, but that's not what I have. I have a KD equal to 0.65 here, so I'm modifying the value in the table by 0.65. My KS value is 0.67, so I'm modifying the value by 0.67. And my KT is 0.85, so I'm modifying the value in the table at 0.6. So in other words, I'm drastically reducing this. In other words, if I would just show this number here, I would take 0.616 and multiply, I'm sorry, 0.161 and multiply by 0.65 and multiply by 0.67 and multiply by 0.85. Okay, this value drops down from 0.161 down to 0.5 to 0.6. That's how much it loses its strength because of these other conditions. Okay, and therefore the bearing length, like in other words, if this was all 1, the bearing length would be much different than if these are no longer 1. Is that okay?
Sir, I have a question.
Yeah, go ahead.
Yeah, so like now this class we went over joist designs,
Go ahead,
right?
Adrian. Feel free.
So,
Go ahead.
so we went over joist designs, and I was looking at the project outline, and it says joist design for the ground floor. So when we did this
What's your
class,
question?
do you hear me well?
Somebody said they had a question. Was it you, Adriano, that had a question?
Yeah, sir, do you hear me?
I can't hear.
Sir,
Yeah, sir, do you hear me?
Somebody
can't hear.
Somebody said they had a
can't-
question. Am I
I can't hear you.
dreaming or am I hearing things?
Now that we went over joist designs,
Yeah.
for the project, the second
Well,
step
I'm gonna do that right now. Okay. So for the project, I'm gonna open up another PDF and we'll talk about the project for the last 15 minutes. Okay. Is that okay?
Yeah, sure.
Okay, so we will be doing the project right after this. So let me just make sure
Okay.
everybody's okay. So I think I sent you a lecture already on this class. I think I've already done that, right? So I'm going to close this.
Yes.
Okay, so what I'm going to do is I'm going to we're recording, so I'm going to now, okay, I'm going to go to the screen share. Okay, so guys, here we go. Okay, so Adrian, I'm glad you brought up the lab because that's the last thing I want to cover, but it's going to be a very short lab because, okay, so let me just start with the slideshow. Slideshow from the beginning. Okay, so here you go. So basically, last week, right, we decided, I don't know if you guys remember, last week we decided that, well, this was the overall size of the home, okay? And let me see if I can annotate something here. Okay, I love annotating on these slides. Okay, and if you remember this, so this is the foundation wall that goes all around the house, okay? And we said that the foundation wall is gonna help, you know, support the floor joists, of course, and we decided to put the beam down the middle, okay? So therefore, this ended up being the joist that we need to design, and therefore this now becomes a span for my joist, fair enough. And we also determined that our dead load was 1.0 kPa, Okay, I hope you guys were able to come up with that value. I mean, and we know that for a residential house, the occupancy load, the minimum occupancy load that the National Building Code requires is 1.9 kPa. So here's my dead load, here's my live load. And on top of that, I do strongly suggest you start with a spacing of 400, okay? Start with a spacing of 400. That's okay. So use a spacing of 400 because that's the typical spacing we put on a house. Now, if you start at 400 and all of a sudden you can't find a joist, like a 2x12 will not work, then you can maybe redo your calculations with a spacing of 300, okay? But start with 400. Don't use 600 for floor joists. It doesn't make sense. Use 400. And of course, because like we talked about last week, okay? Because we're going to have a plywood subfloor, okay, and here's our floor joists, okay. Because we have a plywood subfloor, and the plywood subfloor is going to be at least it's going to be 5/8 inch plywood, and in order for a case 2 system, we need only a minimum of 3/8 inch plywood. We know that we respect that, and we're going to be specifying the nailing schedule on our drawing that the carpenter knows that he's going to have to put the right number, the 2-inch nails, blah, blah, blah. That we'll put that in our spec. So we know that we're going to be able to create a case 2 system. And on top of that, we know that right along here, we're going to have a header joist. A header joist is the same, it's the same piece of lumber that you put here. And it's just that when you put your pieces here at every 16 inches like this, okay, what you do is you nail into right across here, you put your nails, and then this is going to keep that stable. We know that the sheeting with the nailing is going to keep that stable. So we know that our KL value is 1. And of course, we know that we're designing for live load. We know that the KD value is standard, so therefore it's 1.0. We know that we're going to be in a nice dry environment. So we know that our KS value is 1.0. We know that we're going to use untreated wood because we're not going to waste our money on having to treat the wood that's not going to be subjected to a durability factor. So and we know that our KL is 1 and so on, and therefore we can go straight to the tables, and we know we have a system 2 that we can actually create because of the situation, because of the plywood and everything else. So I can go straight to the table and pick my joist, okay? So clear all drawings. So, so now after that, of course, because I'm putting gypsum on the underside of the floor because these people want to have a finished basement, my deflection criteria is going to be not only L over 180 as required by code, but I will also check it for L over 360. And like I said, laterally supported by the subfloor. So everything is 1. Deflection L 180, L over 360, check for both, see which one governs. And then after that, pick your joists, okay, and tell me what you picked. In other words, make sure you use SPF number 1, number 2 lumber, always. That's the species and the grade you're going to be using for your floor joists. And that's going to be it. And that's going to be, and then I'm going to ask you guys what you got. I have a pretty good idea because I already worked this out myself, and I have a good idea what you should be getting. So let me know what you guys end up with for your project, okay? And like I said, do the assignment also, because the assignment is definitely going to get you prepared for the test. And, the test is only 3 weeks away. So start getting ready. You understand? And that's all I have to say about this lab. So there's the geometry. Okay. I don't know if you guys want to do a screenshot and take a screenshot of that, so you have the information and so on. Just take a screenshot. You guys know how to do that. So I won't bother sending this lab. Do you guys want me to send you the lab? I can send you the lab. What do you guys want me to do? Take a screenshot?
Up to you, sir. I took a screenshot.
That's
Oh,
it.
I
Take
took
it.
screenshot.
Take a screenshot because that's all you need. Because look at this. Look at the next slide. You're gonna love the next slide. Isn't that nice? Compared to last week, isn't this a short lab? Right?
I think.
Okay, so guys, that's it. And so let me stop. Let me stop sharing. I want to stop the recording. Okay, or I'm gonna pause it. Let me